Okay, we will try to conclude the remaining aspects of permanent magnet machines in this lecture. And so far what we have done, we revised the permanent magnet materials. We also identified what are the special features of permanent magnet systems. You have a remnant magnet flux density, coercivity, and we also consider the permeability, which is we call it as recoil permeability. So, the slope of the recoil line, as it is demagnetized, that is what you have. Okay. And then we said that the applications we find them in many machines from small to big, for generators and motors. Even it can even be used for some transducers like tachometers, etc. See, if you can even have a permanent magnet tacho generator, because if you have a coil voltage is proportional to the rotation, because it always have a constant flux, etc. Okay. Okay. In fact, it will be since it's a new topic, you will understand better if you do some numerical examples. So, from I can only give you can note down these assignments, right, from the textbook, Electric Machines by Fritza King Stillmans, 1.32, 1.33, 1.34, 1.35. These are the problem numbers. I suggest you can try. This is on permanent magnet materials. Then on synchronous machines, 5.34, 5.35, 5.36. On DC permanent magnet DC machine, 7.24, 7.25. Okay. And as we already know that the PM characteristics are decided by the third quadrant of the BH loop, and if this is the B and this is the H, okay. I wanted to give you there are some curves which are given in literature about the BH in this area. For example, the best material neodymium iron boron will have a coercivity of about so this is about 1.25 or something, okay, and sorry, remnant B, and the H, which will be amperes, sorry, kilo amperes per meter. This is around minus 950. So, you can say this is the sort of a line for neodymium iron boron. Okay. This is the material, and if you go to samarium cobalt, which is next, which is around 0.95, and this is around 700 or something, or 680 or something. I am just giving an approximate figure. So, this may be samarium cobalt, samarium. This is the type of characteristics that you have. Then ceramic, which is low, is around 0.4 going to around 250 or something like that. So, it may have some ceramic, right, and Alnico 5 will have around this is, let us say, 50, and this is about 1.25. So, this will be Alnico 5. Okay. Now, for this Alnico 8 is somewhere in between. It's typically around 0.8 and coming somewhere in between. So, this may be, just give me an approximate figure, but you can look it at Alnico 8. So, you will notice that if you want any system to operate, so you will have a load line corresponding to whatever load you connect externally, and the operating BH would depend upon which material used. So, it may be one of these materials. Okay. And you are also told that you can have a family of the constant energy line, constant BH. Okay. And you may find that maximum, I am just telling you. So, wherever it is tangent to that curve, that will be the point of constant or maximum BH. Okay. Why constant BH? That will tell you energy density for that magnet material. So, maximum energy that it will give is not neither here nor here, it is the product of B and H. So, somewhere in between you will have. Okay. So, you must draw a constant BH line and then find out what is the value, etc. Okay. Because we also discussed if there is a BH curve, we said that at any point where you have a alloy to disconnect, so there is always known as a recoil line. And slope, you call it as mu recoil, okay, which is used as a sort of permeability for that portion of the magnetic circuit. Okay. Right. Now, let us go back to the sine wave synchronous motors, certain aspects. In the last lecture, what we said was sine wave synchronous machine will be considered as similar to a conventional synchronous machine, but the field is fixed now. Flux is nearly constant by the magnetic field, and if it is unexcited, there is a synchronous reactance excess. Okay. This is the synchronous reactance, that is, if the armature windings are excited by polyphase currents, it will give rise to a magnetic field. The flux per pole divided by the current is an inductance linking the winding. Okay. right, and this is a sine winding, and we do not take it our leakage inductance. Okay. But this equation is modified if you take Fourier series and harmonic winding factors also. Okay. We are taking fundamentally into account, but there may be harmonic fields. Now, ideally what we considered was there is a sine wave distribution of the conductors, and which will give rise to these fluxes. Okay. Conductors are distributed in a sine wave. So, if you have pasted a current sheet on the surface of the stator whose current density will be purely sinusoidal, okay, and that will only give you a pure MMF which is sinusoidal. But in practical case it could even be a stepped waves which will have its own fundamental and harmonics. Okay. So, it is called a sine distributed phase current. But you may know that conductors, there may be n conductors per slot, okay, and it will give a rectangular MMF wave. If something gives a rectangular MMF wave with some peak value f, and what will be its fundamental? What will be its fundamental? So, it will have some fundamental, no? Now, this is 4 by pi f, is not it? A fundamental of a rectangular wave of amplitude f or so will be 4 by pi times f. I hope you have no doubt on this. Okay. You must have done signals and systems and various things. Okay. So, a rectangular wave has a fundamental component 4 by pi of this. So, effectively, a conductor of n conductor per slots can be considered to be 4 by pi n if it is a sine wave. Okay. Then usually you are aware of what is distribution factor for fundamental, isn't it? I hope you know the distribution factor, is not concentrated, distributed, right? Anybody having a doubt on this? Anybody who do not know distribution factor? Okay. So, you know distribution factor, and you know the pitch factor also if it is sharp pitched, okay, and you know the winding factor which will be pitch factor, distribution factor. Of course, sometimes there is a skew angle if it is skewed also. If it is skewing means the windings are not directly parallel from one end to another to the shaft, but it will be by an angle sigma or whatever it is. Okay. And you know that the effective turns will be 4 by pi kW into number of turns n phase. Okay. So, the open circuit voltage, how much voltage induced by the flux per pole due to the magnet will be 4.44 2 pi by root 2 winding factor into number of turns per phase into frequency. You are aware of this. So, this much voltage induced, this is the flux per pole, that is phi m. Okay. Now, the torque you can show 3 times P is the pole pair by omega into EQ into I sin beta. Beta is the angle, torque angle, that is for the motoring. That means there is a voltage into component of this voltage. EQ is the voltage per phase along the Q axis. Okay. And this is the synchronous reactance which includes this is the synchronous reactance which includes the flux due to the air gap, it is due to air gap flux, and this is leakage. This is only due to air gap flux. what it means is if you pass the current, certain flux will only link the and pass through the air gap. Okay. And this will be based on design parameters like poles, gap length, winding factors, turns, diameter, length, and of course the frequency, and mu naught is the permeability. So, there are some which mostly it depends upon the design data, okay, these synchronous reactance. In surface mounted magnets, there is no saliency in the magnet, surface mounted, just mounted on the surface, but sometimes if you make cuts etc., then it will create some saliency, right. There you assume that D and Q, so whatever may be the position of the rotor, the synchronous reactance of the stator will remain the same, because the flux pattern will not change, isn't it. But if it is purely saliency, then it will change, because to that winding whether D axis is aligned or Q axis is aligned, it is of your concern. Okay. The phasor relation between E phase, what is the voltage induced per phase will be J times EQ, right, that is J times omega into flux linkage lambda MD, that you know, right. If this flux linkage in the D axis, then the voltage will be EQ, right, J times this. I mean this is you have to recall some of your machine modeling, okay. You are aware of the phasor diagram of a synchronous motor, right. So, if this is the D axis means your magnet is in this line, this is the magnet. If that is the D axis, then the voltage, no load voltage or the generated voltage will be J times EQ, isn't it. This is along the Q axis, and for that are the, this is the open circuit voltage, for that you add the resistance drop and the synchronous reactance drop. So, J times XS into I, and then you get the voltage V, isn't it. I hope you know this, right. So, this is due to the flux, and this is the D axis and this is the Q axis in the phasor diagram, okay. So, if you have this is the current I. Now, the voltage to current phase angle is, let us say phi, current is lagging like this, and voltage to E, what is the angle, you call it as delta, that is the torque angle, right. This is what you have, this is also called the torque angle, V into E, V and E, okay. Then angle between the EQ, Q axis to I, let us call it as gamma, and I is, and D axis, let us say call it as beta. See, I is at an angle beta from Q axis and angle gamma from Q axis and beta from D axis, okay. These are some of the actors, okay. Now, V phase will be whatever E phase Ri plus J in the phasor, okay. This is voltage, terminal voltage will be this, and from that minus gamma is pi by 2 minus beta, okay, from the angles that we have mentioned, right. and you know that I is ID plus JIQ, isn't it? The current will be ID plus JIQ, and ID is derived from the D axis transformed current when modulated into the stator frequency. Okay, that is what you do. And we have already studied V equal to Vd plus JVQ. So you must recall the DQ transformations which you have studied, right. And ID will be minus I sin gamma from that phasor diagram, and IQ will be I cos gamma, isn't it? ID IQ, which you have already seen. So, this will be ID and this will be IQ. And you know what is the role of ID? ID will be either magnetizing, it will be in line with the flux ID, and IQ will be in line with the voltage. So, IQ is the one which is a torque producing component, ID is the one which will be a flux producing component, right. ID is the flux producing component, it is aligned with flux magnet, and IQ is a torque producing component because that is quadrature to the flux. Torque is produced by a quadrature component with reference to flux, isn't it? Okay. So, you can broadly say that IQ is torque producing and ID is flux producing. So, that will either add to the main flux or subtract to the main flux depending upon the direction. Okay. And the angle phi is delta minus gamma. Of course, gamma you look at the direction which is in which it is mentioned. Now, if you neglect resistance, let us say R is 0. Okay, so it will be VQ, JVQ plus JXSID. Okay, what will be this? This will be VQ and this will be VD. Okay. So, that is the D and Q components of V. Okay. This will be JVQ and this will be VD, right. Because it is written JVQ when you consider VQ as a scalar, okay, and JEQ is where you consider EQ as the scalar, right. Now, if this is the current which is the phase current and it will have a D component which will be I cos beta or I sin gamma, and it will have a let us say Q component and to VQ you add minus XSIQ here and you also add to this XSID, isn't it? You have this is XSID and XSIQ and this will be the V ultimately. So, this will be in this case what are you observing? ID is in line with the D axis. So, this will have a magnetizing effect. So, armature current is flowing in such a direction to magnetize, means to aid the permanent magnet flux when it is loaded. Okay, this is sort of a reaction of the armature currents, right. And there could also be another case, this is a magnetizing, another could be demagnetizing. Look at this case, here I is not here, I is here, right, and V is here. And therefore, this is your ID. So, what is a in this phasor configuration, you find this ID is having a demagnetizing effect. Is it okay? Because they are the components of the armature flux. After all, if you look at a common observer observing the air gap, whether it is a armature MMF or field MMF, they are rotating at synchronous speed. Okay. So, you have a magnetizing effect or a demagnetizing effect. So, ID is positive. If ID is positive, the armature current produces MMF distribution around the air gap that tends to increase the d axis flux produced by the magnet. Okay. And in this condition, armature reaction is a magnetizing reaction. And if ID has a negative MMF, ID is negative, MMF is negative and it has a demagnetizing effect. Okay. We are repeating the same thing. Okay. So, we can write down the phasor equations. So, Vd will be minus V sin gamma, which is minus XS IQ, isn't it? If you look at that curve, sorry, phasor diagram. So, this is minus XS IQ, which is nothing but V, delta, okay. And similarly, VQ will be EQ plus XS ID. Okay, I think you can, it is very easy. That is V, one is V sin gamma and there is V cos gamma. And the torque will be 3 times P by 2 into psi d IQ minus IQ ID. This will be the torque. Interaction of the d axis flux linkage and q axis current, okay, because you know that in a typically you would like to say if this is the magnet, this is the d axis and this is the q axis, you always have the d winding and q winding. Okay. And if you have recall the machine modeling, you know that this each of these will induce AC, this will be DC in steady state and it will induce AC in these windings because they are cos omega t like that. Okay. And when the corresponding one which they produce, when the AC is produced, we call that as the AC component of the D. That means as if you have a DC component having modulated through that AC. Okay. And these are the terms you must be reconciled to. Okay. Then omega, this again under steady state, omega lambda d is EQ plus XD ID and omega lambda q or omega psi q is XQ IQ. Okay. These are again the terms you are expected to know. Okay. So, torque, if there is a, you know, if there is a saliency, we use XD XU, right, and the torque expression will have, will be, one will be EQ IQ, another will be XT minus XQ into ID IQ. And I hope you are aware of these two components of torque in saliency presence, in the presence of saliency. And this is called, normally called electromagnetic torque, and what is second one called? Reluctance torque, because it is depending upon the difference between XT and XQ. Okay. And this may be present in permanent magnet machines, but in surface mounted machines where the air gap is smooth, then you can take it as XS. So, XD is equal to, if reluctance torque is 0, this is the torque which is a product of EQ and IQ. This is a torque component, right. Now, EQ depends upon what? EQ mainly depends upon psi d, or that is the flux per pole produced. So, torque, if EQ is constant, so torque will be proportional to IQ. So, extra torque is produced if the from the stator if IQ is fed, okay. And you know, in all these places how are you feeding? You are feeding through converter, isn't it? Okay. So, if you want to have a little understanding of this, here is a DC source which will feed these windings, isn't it? Okay, through the converters. And you are aware that it will be. So, this is a DC source through the converter VC or something, and there is the current that is, after all this whole thing is a converter, isn't it? Right. Now, in practical cases you can control the frequency. So, you can make a, you can control F and speed, that is what you do. If you want a variable speed for the such motors, isn't it, you control the voltage, control the speed, okay, and you can have from low frequency to high frequency. Now, what are the limitations in these things? Your flux is, air gap flux is limitation. What others are limitations? I mean, you can't pump any type of, any amount of flux. What is other limitation? Current is the limitation. Current in the windings, and also you may be aware that these devices also have certain capacities, isn't it? You know what capacity of devices you must choose, right? And how do you rate the devices? How is the rating of a device? What is the voltage it will be able to withstand when it is off, current it will be able to carry when it is on. I think you seem to have a product of these two, okay. So, sort of an open circuit voltage into short circuit current or whatever it is, right. So, switch ratings are somehow decided, okay. Now, how much you start driving the motor and you go on apply certain voltage through this, obtain a frequency through this, and then you go on loading it. What are the factors up to which you can load the motor? Can you go on loading as you like? What is the limitations? You can go on loading the motor till the winding currents are limited in the motor, till the operating flux is constant, and till the device ratings are not exceeded. So, they are all the factors. Say the even the converter voltage is fixed. So, you have VC here, converter voltage and the current it can feed, devices it can take, another thing. So, from all these point of view we can have a qualitative explanation how much torque it can give as the frequency changes. Normally you can maintain, it is basically torque is, you say, approximately equal to IQ, isn't it, so long as EQ is constant. So you may know the so called V by F control. You know the V by F control for the motor, right. So you can more or less maintain, here is flux constant, can go up to certain point. So this is torque constant, a constant torque operation up to certain frequency, let us say omega q. Okay. Then what will happen is, beyond that the current drawn, if frequency increases, and this will have a sort of a demagnetizing effect beyond certain point. So there will be underfluxing, speed of course increases, but torque will decrease, because when underfluxing means torque is proportional to IQ and flux is decreasing, right. Till that time flux is constant, here flux is changing, isn't it. So the armature current will be such as to oppose the magnet flux, and you can go up to certain frequency, beyond which it will not be capable of supplying the torque. Okay. I mean, you may be aware of similar curves even in other machines, induction machines, DC machines, etc. There is certain range where you maintain the flux constant, current constant, so torque constant. But beyond that you have to do, even though the current is constant, it will be demagnetizing. So one will be a constant torque zone, other will be typically a constant power zone. Okay. So this is a torque speed. It is cannot be called characteristics. It can be called as torque speed capabilities, right. This is, you can say, capability. How much the machine is capable of generating. Okay. So the surface mounted motor has very limited capacity to operate above its corner point speed and cannot maintain constant power characteristics as the speed is increased, right. So you can't go very high speeds. Okay. So fundamental physical reason for this is that air gap flux is fixed by the magnet, and direct field weakening is not possible, unlike in wound field machines. Okay. Then resistance is neglected, but in practice it introduces phase shifts which makes speed torque envelope more restricted. Especially very low frequencies, resistance become very good component of the thing. Okay. In fact, you can visualize for the same voltage, and synchronous reactance will go on changing, and the generated voltage will be appropriately modified. Okay. Because it is a balance between generated voltage, terminal voltage, and the synchronous impedance drop. Okay. That is what decides the characteristics. Another thing, torque per ampere, how much for a given machine, how much torque you can get per 1 ampere of excitation. Okay. In both in sine wave and square wave. In sine wave motors, torque per ampere as a derived expression, this is the flux density B. Okay. For a given flux density, this is the factor, okay, and for a maximum beta is pi by 2, the torque angle is pi by 2, this is the 3 by 2 root 2 pi R1 L B Ns by 2. Ns is the number of conductors, number of turns. Okay. So, this torque angle is positive for motoring, which is taken as this one. So, this for sine wave motor. Sine wave motor, this is the torque per ampere. For square wave motor, torque per ampere will be 4 N phase Bg LR1. This is, this is the fundamental, this is RMS. In square wave, with 120 degrees, if this is the current, then the RMS will be root 2 by 3. Okay. See, you may know that while the average value may give you average torque, RMS value is the one which which decides the heating in the coils. So, RMS and average will have different impact on the motor. Okay. So, torque per ampere for square wave, this is RMS, because this was the peak. So, torque per ampere for the RMS is like this. So, torque of a square wave motor exceeds of that of sine wave motor by a factor of 1.47 for the based on the assumption of equal peak magnetic flux densities in the air gap. For the same, because we are assuming square wave motor, the B is sinusoidally changing in space. In the case of square wave motor, B is nearly constant in that one. So, there is you have noticed that square wave motor is expected to give a higher torque. Okay. Now, we can consider the volt ampere requirement, right. Now, you have a motor, and what should be its volt ampere requirements for variable speed, and what should be the VA requirement for the converter. Okay. So, I think these are some practical problems, because the permanent magnet motor invariably operates through a converter. Okay. And you have to find what rating. If you want to operate a say 10 kilowatt machine, what should be the rating of this? Now, there are some relations are given here. I think basically the RMS kVA per kilowatt is 2Q IS the switch current. IS is the RMS current in each switch. Okay. Each switch there is an RMS current, okay, and small is the peak current in each switch that is flowing through. So, the peak kVA that you can have, peak kVA required per kilowatt is 2Q IS. Why 2? Because 2 switches are operating at any time. Okay. So, Vs is the peak voltage across each switch, right. So, this is the rating of the converters. Okay. For sine wave, RMS switch VA is 6 VI by root 2. For peak switch VA is 6 VI, where I is the peak current, because there are 6 switches. Okay. Then converter power output will be 3 times V by root 6 into I. Okay. For square wave, the RMS switch VA is 6 times VI, because root 2 by 3 is the 6 times V into I RMS, okay, that is I into root 2 by 3. Peak switch VA is 6 times Vi, that is for a square wave, because V is the voltage and I is the current, square wave current, and converter power output is Vi. Okay. These are some practical aspects of the rating of the converter and the motor. Now, RMS switch KVA per kilowatt is 4.9 and peak KVA per kilowatt is 6 for square wave motor. That means, what does it mean? If you have 1 kilowatt motor, you may have to have a 4.9 kilowatt converter switch, okay, and or a 6 kVA for square wave. Then RMS switch kVA per kilowatt is for a sine wave motor, it is less. Sine wave motor, see, one of the things you realize is sine wave motor, the rating of the converters, RMS switch per is 3.5 and peak kVA is 6.9 for square wave motor. Okay. So, I think these are some aspects, and I suggest for, I mean, this was only to provide you a glimpse of some of the issues involved. So, I think only way is you read, I think this is reasonably good book, okay, where these are given in detail, that if you, with this you just scan through this, and that should tell you. And also there are some numerical examples given at the end of the chapters in this book. I recommend that you try this. If you, they are not very complicated questions, but they are more substitution type. Okay. So, I think we have more or less covered some aspects of which are salient aspects of permanent magnet motors, because you know that almost you can any topic you can cover one course. Okay, you can have one course on stepper motors, you can have one course on reluctance, switch reluctance motors, one course on permanent magnet motors, one course on single phase motors, etc. Okay. Anyway, we have in this course, which is named as special electromechanical system, which is supposed to be complementing your knowledge on other electromechanical systems, conventional ones which you have studied earlier. Okay. So, broadly what we have discussed here is induction machines, right. Then we have discussed reluctance machines, and then permanent magnet. This is what we have broadly discussed. Okay. And we have on induction machines, our center was single phase motor, because as of now they are the one which is having the maximum use both in domestic and small power ranges. Okay. We also looked at 3 phase machine, unbalanced, asymmetrical. Okay. All this we have discussed. I am just trying to review what is it that you know, you can go back, recap what you are supposed to have learned, right. And you know, a lot of theories were there, double Riemann field theory, cross field theory, and so on. Okay. And then we also looked at induction generator, because that is grid connected and self excited. This is what we have discussed. Then we looked at the switched reluctance motors. And which has a variant in stepper motor also. Right. Now, we knew that the switched reluctance motor, you go on, all you do is you go on switching the windings in the stator, so that the rotor, which is not magnetized, but it has a variable reluctance, it tries to align with the magnetic field produced by the stator. And stepper motor also has a similar concept, but stepper motor operates at low speeds and for high torques, and switched reluctance motors are maybe continuous speed, etc. And again, the associate theories will be basically variable inductance in the windings, okay, and inductance variations, saturation, all these things comes. There are some machines where saturation seems to be, or nonlinearity seems to be very predominant, like self-excited induction generators, switched reluctance motors, permanent magnet motors. Okay, nonlinearity is inherent in them. Okay, where in other conventional machines you can tend to neglect or those nonlinearity. Okay. Then of course we discussed about permanent magnet, which has generator, motor, and which has synchronous, DC, brushed, brushless. Okay. There are varieties. I am just trying to see the what it is about. Okay. Now, there are others, which perhaps which may be relevant for you to know. One is the hysteresis motors. And there are disc motors, and there are linear motors. There are also universal motors. Broadly, they are also used. Hysteresis motor is sort of, in rotor they use the hard magnetic materials, so that when the stator induces a magnet in that, okay, and it works as synchronous motor. Disc motors, for your vacuum cleaners and so on, you want something which is a disc type. Even wind machines, they are also planning to disc type and conventional type. What is the difference? I hope you know about disc motors. In disc motors, currents are radial and flux is axial. In conventional machines, the current is axial and flux is radial. Okay, and linear machines, both current and flux are linear. They are nothing radial in a way. Okay, and for example, now the most fashionable high speed trains are maglevs, or magnetically levitated trains. The linear machines are being used, okay, where you spread out, and every machine can be made linear, and perhaps every machine can be made a disc machines. Okay, and application scenario for special machines appears to be very, very large. Okay. So, if you introspect and can you visualize that number one is, what is the importance of the study of what you have undergone? Do you think it will have any meaning, or it is only for passing your examinations or get some grade, or do you think it is likely to have a lot of impact in technology for the future? Okay. So, there are some other things which I mentioned sometime, the futuristic aspects. One thing which will become very critical will be energy conservation, energy efficiency. So, every system that you make, if it was consuming X kilowatt, you must try to see tomorrow it should consume less than X kilowatt. Okay. Then you are likely to have more electric movements than mechanical movements. So, there will be more electric ships, more electric aircrafts, more electric cars, and more electric trains. So, everywhere these machines, these special machines will find a way. Okay. And renewable energy, as I told you, will have a impact because you must have a power generation through these sources, whether it is wind energy, small hydro, biomass, hydrogen energy, fuel cells and other things. So, they will all require electromechanical systems. Now they are talking about the so called micro turbines, as I mentioned. So, you have to be alert if you want to be excited by technology. And there have been we have tried, this course is supposed to take you to the periphery of some of these topics. Okay. We may not have gone into deep in any of the topics, but exposure is what is planned or what was aimed at. Okay. And you have to be alert in terms of what is going on in the field by looking at the technologies as published in technical literature, or they can be in other industrial documents, patents and so on. And I think there are a lot of exciting developments are possible in this area, because as the name indicates, the topic is special. Okay. So, I hope it has make you think and excited you. So, with these concluding remarks, I think we will close this series of lectures, and hope that you will have some hysteresis left with you over a period of time based on this series. Okay. Thank you very much.